Hello and welcome back to Guillotined 18th Century Chemist Theater. Today we are going to start our stoichiometry unit, and to do that we're going to review a couple basics that we'll use to build up to stoichiometry. So in this lesson we actually won't get to a stoichiometry problem, but we'll talk about some of the concepts of stoichiometry and some of the things you want to prepare for so that you can be successful at this. Really one of the key skill sets of chemistry, and if you've been following along with the video series, we've been working towards this for a while. And so, got our old friends, of course, the Walrus and Amadeo are back here for old-time viewers. Really, stoichiometry is sort of like a review party. It's a reunion episode where everything that we've come back to, or everything we've learned is coming back again. And so really, we're exploring mass and amount relationships in a balanced equation. Meaning we're going to take a balanced equation, which is written as a mole ratio, and we're going to incorporate molar masses so that we can actually measure out the amounts needed to do this. And so really, typically, and there's a lot of different ways to do a stoichiometry problem. Don't get hung up on this way, but the classic stoichiometry problem typically involves molar masses and, of course, a mole ratio. We'll need a balanced equation. And so this is what chemists use to figure out the big questions of why people get employed. The idea of, hey, listen, I need to produce this much stuff or I have this much stuff left, and how much can I make from that? And so it really takes the world of measuring things in the laboratory and incorporates it into the world of balanced equations. So it's really all about setup. We'll be using factor label and using some of the formats we've talked about before. But once you set these up neatly and nicely, they come along quite well, and you'll be quite successful with this. And so typically what's going to happen is in a chemical equation or in some kind of laboratory condition, you're going to want to find the grams of a second substance given grams of a first substance. Either this is like saying, hey, listen, I've got this much of reactant A, how much reactant B do I need? Or maybe someone will say like, hey, I have this much reactant A, how much reactant C am I going to need, or D to produce? So there's lots of different ways to look at stoichiometry. But typically, it doesn't matter whether you're dealing with reactant, product, reactant. It doesn't matter what way you're looking at it. Typically, you're given grams of one to find grams of another. But we can't do that easily in one step. And so what we're going to do is we're going to take a slightly more circuitous route, and that's incorporate the idea of moles. Because once we get to moles, we can use the balanced equation to tie these things together. And so classic problem is you're going to get to moles of that first chemical, you're going to use the balanced equation, work your way through, and then get to grams of the other one. Sort of consider moles like an underground world, not unlike the mines of Moria or something in Lord of the Rings. And the idea is that we have to get down into this world of moles. And if we can make it through that, we can come back out wherever we want to a measurement in our laboratory. And so classic problem, we're going to deal with molar masses and mole ratios. But anything that can get us to moles can start a problem. So we don't have to start with grams. And we'll talk about some of that later, of some of those twists you can do. So let's review real quickly the idea of molar masses and mole ratios. And so Amadeo will take over, and we'll talk a little bit about molar masses, just to review this for a second. And so again, typically we're going to start with grams and go to moles, and then we'll have moles at the end and have to go back to grams. And so we'll have to do molar mass work. So feel free to pause the video right now and work through this problem. The idea of 57.8 grams of water, how many moles of water is that? That's typically what we're going to need for a problem like this. So go ahead, we'll wait for you. Hey, welcome back. So to solve this, we will need the molar mass of water. And if you don't have that memorized already, we'll go to the periodic table, and we will pull off the molar masses of each element and do the work. Now remember, I like to show all the work, but if you're doing back of the envelope sort of stuff or doing something laboratory, you can obviously skip showing the work, but let's show you how to do that. So that's the molar mass of water. And so remember what that tells us. If we had 18 grams of water, we would have a mole, or 6.02 times 10 to the 23rd molecules of water. And so I have 57 grams, so I should have a lot more than 1 mole. So we're looking at about 3 moles. And so if we do the math, 57.8 divided by 18.02, we end up with a little over 3 moles of water. And that makes sense because every 18 grams will give you 1 mole. And we're going to incorporate that into a larger stoichiometry problem next time. But let's just review some of this stuff. Okay, so what's the mass of 2 moles of calcium carbonate? Which again will be sort of the backside of a stoichiometry problem. We'll end up with the moles of a product and then have to convert it to grams. So again, we'll pause the video. Welcome back if you went ahead and did this. So let's figure out the molar mass of calcium carbonate again. 1 calcium, 1 carbon, 3 oxygens. Again, I like to pull my molar masses off to the hundredths place to stay consistent, but of course it's up to you. So I end up with 100.01 grams per mole, and so if I have 2 moles, again, we don't even have to set up the work. I have 2 moles at 100 grams apiece, so that would be 200 grams, but let's show the work. Moles cancels out, we have grams. And so you'll see that a lot. You'll see a lot of molar masses in a typical stoichiometry problem, but there's a lot of atypical things you can do with stoichiometry. Now, the new thing is the idea of using balanced equations to come up with mole-mole ratios. And really, in my opinion, this is what makes a stoichiometry problem. Even if you just had a mole-mole ratio, you'd have a stoichiometry problem. And so it's a matter of what we're going to use to get to moles and what we're going to do once we have moles. And those conversions are typically molar mass, but again, whatever you want to do. And this is where we're going to start running into not having the number 1 in front of moles in our conversion. Typically, we've always had 1 in front of the moles. Moles per gram or moles per atoms or things like that. And so what we'll do is we'll get a balanced equation. So again, feel free to pause the video, balance this one out. Welcome back. And so let's balance this bad boy out. So we end up with a 4:5:4:6 ratio. And remember what that means. That means for every 4 ammonias, I would need 5 diatomic oxygens, and that would produce 2 nitrogen monoxides and 6 water. Whether that's molecules or moles, whatever the scale would be. And so don't really worry about what's a reactant or what's a product. The math isn't going to change. Reactants get consumed and products get produced. But let's see what we can do with this mole-mole ratio. So if I have 12 moles of ammonia, how many moles of diatomic oxygen would I need to react with it, and how many moles of each I would produce? Well, again, without setting up a math problem, if I go from 4 moles to 12 moles, then I'm going up by a factor of 3. So you could easily assume everything else would go up by a factor of 3, and so I would need 15 moles of diatomic oxygen. I'd produce 12 and 18 moles of each product, respectively. But let's show you how to do that mathematically. And this is the only thing you really ever need a balanced equation for, are these mole-mole ratios. This is the reason why we balanced equations. So mathematically, what we've done is we've done the exact same thing you reason through in your head. For every 5 moles of diatomic oxygen, I need 4 moles of ammonia, and that's what that conversion states. And so I just multiply that out, and I end up with 15 moles of diatomic oxygen. And so understanding why we have mole-mole ratios really is going to strengthen your ability to do stoichiometry. Again, for nitrogen monoxide and ammonia, again, it doesn't matter that the nitrogen monoxide is being produced and the ammonia is being consumed. It really doesn't matter. I will produce 12 moles of that and 18 moles of oxygen. Again, dealing with the same idea of, well, for every 6 I need 4, or for every 4 I need 4, whatever the case may be. And you will always see a mole-mole ratio in a stoichiometry problem. And so what we'll do next time is we'll take these 2 simple ideas of molar mass and mole-mole ratios, and we'll tie them together into a full stoichiometry problem. And once you get the hang of this, stoichiometry problems are really pretty simple. You've put your time in. You've learned a lot of stuff so far about factor label, about conversions, units, sig figs, molar masses, balanced equations. All of this stuff is about to pay off. So congratulations, and we'll see you next time. So thanks for watching, and have a great day.